Hi, welcome to Statistics 1. And this is the first lecture where we'll talk about randomized experiments and observational studies. A lot of first courses in statistics start with the distinction between descriptive statistics and inferential statistics. We'll do that as well, but I'll do that in the second lecture. What I'd like to do in this first lecture is instead make a distinction in how psychologists and behavioral scientists and many scientists, for that matter, apply statistics. And there's a main distinction between experimentalists and differentialists. So experimentalists use randomized experiments. Differentialists tend to rely on observational studies and correlations. It's important to understand this distinction because those two types of researchers use statistics in very different ways. So what I'm going to do in this first lecture is just talk about the difference between a randomized experiment and an observational study. So this first lecture will be organized into two segments. The first, I'll give you a couple of examples of randomized experiments. In the second, I'll give you a couple examples of observational studies. So in this first segment, let's talk about randomized experiments. And at the beginning of each segment of each lecture, I'll show you important concepts to take away from that segment. In this segment, the important concepts to take away are the idea of random and representative sampling, independent and dependent variables, double-blind and single-blind experiments, and then the idea of confounds. And the most important concept to take away from this segment is the idea of causality. So I'll both begin and end this segment with causality. The major benefit of randomized experiments is they allow us for strong claims or strong arguments about causal mechanisms. And my whimsical phrase for this in my lectures at Princeton is they allow us to say something about why stuff happens. So in life, lots of things happen, lots of good stuff happens, lots of bad stuff happens. If we can understand systematic patterns and we can conduct randomized controlled experiments, then we can start to understand why stuff happens. And if we can do that, then we can predict stuff. And if we can predict stuff, then we can prevent the bad stuff. We can promote the good stuff. And the example I use for this in a lot of my classes is the movie Forrest Gump. So I'm sure a lot of you have seen the movie Forrest Gump. And even if you haven't seen the movie, you probably know this famous line from the movie where Forrest Gump, the Tom Hanks character, says, "Life is like a box of chocolates, you never know what you're going to get." And I don't like that line. In fact, I didn't really like Forrest Gump the movie. I know that's horrible to say, almost everyone loves that movie. But I didn't like it for that reason, because I don't think life is like a box of chocolates at all, at least mine isn't, because I am a statistician, I'm a scientist, I know where the good stuff is and I know where the bad stuff is. So it's not, for me, like a box of chocolates, it's even better than a box of chocolates, because I know where the good chocolates are and I know where the bad chocolates are. So I can prevent picking bad stuff and I can promote getting good stuff. And randomized controlled experiments allow me to do that because they allow us to make claims about causal mechanisms. Now, in order to do that, we have to have true independent variables, and I'll explain what I mean by that in a moment. We have to have random and representative samples in our experiments. And we have to have no confounds in the experiments. And that's an impossible ideal, but good scientists, good experimentalists do their best to get no confounds. And again, as we go through the examples, I'll talk about what I mean. So we'll start out with two examples of randomized controlled experiments. One is a classic, the Salk vaccine trials to eradicate polio in the United States. And then I'll talk about a recent set of experiments on what's called working memory training. This is a new wave of research in cognitive psychology designed to enhance intelligence. But first, let's start with the polio vaccine studies. And before we do, I just want to walk through a few definitions. Hopefully, a lot of this is review, but if you haven't seen these definitions before, if any of this terminology is new to you, make sure you understand what these terms mean. So when we talk about experiments, and as we dive into the statistics of this course, which will happen right away in Lecture 2, I'll just start to use examples. And in those examples, it's important that you understand the difference between a population and a sample. So the population is just the entire collection of cases or people that we would like to generalize about in our research. A sample is just a subset of that population. So in the first example I come to, we're going to talk about vaccine trials that were conducted by the US government to eradicate polio. In that example, the population is all children in the United States. They wanted this to generalize to all children in the United States. They couldn't get their hands on all children in the United States, so they tried to collect a random representative sample, a subset. It's also important to know the distinction between parameter and statistic. So parameter is just a numerical measure that describes some characteristic of the population, and statistic is a number or measure that describes some characteristic of a sample. So parameters, populations, statistics, sample. This distinction is where most stats courses start off. Most statistics courses, most textbooks on introductory statistics will start with this distinction between descriptive and inferential statistics. And I'll do that as well. We'll start with descriptives in the next lecture. But again, I think it's more important to start with a distinction about how statistics are used. But it is important to remember descriptive statistics just describe sample data, and inferential statistics are procedures that are used to make generalizations from samples about populations. And finally, we'll see this in the examples, but it's really important to make this distinction between independent and dependent variables. This is, again, one of these odd things that some students get mixed up at the beginning of a statistics course, and they get flummoxed in the first few lectures because they keep reversing these. But it's as simple as knowing your right from your left. You just have to know it. So the independent variable is something that, as an experimenter, you manipulate. So in the polio vaccine example we'll cover in a second, it's just whether the child was administered with the vaccine or administered with a placebo. The dependent variable is what you measure. It's dependent upon the treatment. So in the polio example, we'll look at rates of polio in a certain sample. Okay, so let's talk about this example in some detail. So in the first half of the 20th century, polio was a very scary disease all around the world. And in the US, there were about 20,000 cases per year. It fluctuated a great deal per year. Some years were worse than others. It was a contagious disease, so some years were particularly worse than others. In 1952 is a good year to point out, there were 58,000 cases of polio. That same year saw the development of the first effective polio vaccine. It was developed by Dr. Jonas Salk, and a lot of these first randomized experiments are known as the Salk vaccine trials, named after Jonas Salk. And how do we know that these trials were effective? How do we know that the polio vaccine was effective? Well, we know they were effective because of randomized experiments. And the way those experiments worked was in the following manner. First, what's our population, what's our sample? As I said, population was, we want to generalize to all children in the US. I mean, ultimately, we want to generalize to all children across the world. But in these first sets of studies with the Salk vaccine, this is funded by the US government. So the population, we could consider it to be all children in the United States. The sample at first was just 4,000 children in the state of Virginia. That's clearly not a random and representative sample of all children in the US. Right? There might be certain characteristics about kids in Virginia or the culture in Virginia or the certain communities that they sampled. So eventually, once they started to see evidence that this was effective, they expanded this to 44 states, including 1.8 million children. Then they clearly had a representative sample. But first, it was just 4,000 children in Virginia. The independent variable, again, was whether the child received a vaccine or whether they received a placebo. So the way that worked is a child would receive an injection, and one was a live vaccine, the other was just a control placebo. The dependent variable, we can think of this as being measured two different ways. One, we could measure at the level of an individual child. So at the level of an individual child, it's just, did that child go on to be diagnosed with polio at some point or not? So at the level of an individual child, it's just 0 or 1. No, they were not diagnosed. Yes, they were diagnosed. What I'll be showing you is rates of polio in groups of children. So what's the rate of polio across the United States after the introduction of the vaccine? The other nice thing about this as an example to start with is this is what's called a double-blind experiment. So the experimenter, or the person who's actually administering the vaccine, actually didn't know if they were giving the live vaccine or if they were giving the placebo. And the child and the parents who consented to allowing their children to participate in these clinical trials, they didn't know if the child was getting the vaccine or not. In the double-blind cases, there were some cases where, in the Salk vaccine trials, where they did know. But the one I'm describing here, it was double-blind. The benefit of double-blind is there's no bias from the experimenter or from the children themselves or from the subjects in the study. If it were just single-blind, then just the experimenters would know, but the children wouldn't know. And here's the result of one of the first Salk vaccine trials. If you look at the rate of polio per 100,000 children after introducing the Salk vaccine, those who got the treatment, those who got the real vaccine, there were only 28 cases per 100,000 compared to the control, where there were 71 cases per 100,000. So the rate of polio was cut in half. In fact, in more than half. And as these trials expanded, and as more and more parents consented to having their children get the Salk vaccine, and then even better vaccines were developed, polio by 1994 was completely eradicated from the United States, not just the United States, but all of the Americas. So this is an incredibly successful story of government intervention in preventing a disease, and as I said here, prevent bad stuff. By the use of this randomized experiment, we saw that the vaccine was effective, and once parents were convinced that this worked, then parents consented to having their children vaccinated, and an entire disease was eradicated completely from the Americas. Now let's move to an example not quite as serious and more contemporary. So this is a very hot topic of research in cognitive psychology today. It's called working memory training. The idea behind this is that we could have people come to our laboratories, engage in these computerized tasks that test their working memory about a half an hour a day. And by doing this every day for weeks, sort of like going to the gym every day for a month or two, you can enhance your intelligence. Just like by going to the gym every day, working out, you can get in better shape. This is a pretty radical idea within the field of psychology, because conventional wisdom up to the last sort of decade or so is that once you become sort of an adult, once your brain is matured, once you reach about 18 years old or so, that your level of intelligence, your working memory capacity is sort of fixed relative to the rest of the population. Some new results are showing that that might not be the case. And we might be able to put you into these specific training environments that will enhance your intelligence. So the idea here is, let's promote the good stuff. Intelligence is a good thing. So in these randomized experiments, the population is just all healthy adults. We want to be able to generalize these results to all healthy adults. The sample should be random and representative. So we should get a range of individuals from all sorts of different backgrounds, certain educational backgrounds, different levels of intelligence, so that it's representative. And then we should have random assignment to conditions. So if we look at the structure of the experiment, the independent variable is whether subjects receive training or no training. So they should be randomly assigned to get the working memory training, or get some sort of control training or no training, which is in the example I'll show you first. And the dependent variable is their change in intelligence. And the way this was done in the study I'm going to show you is the experimenters measured subjects' intelligence in a pre-test, had them do training, and then measured intelligence in a post-test. So the dependent variable here is change on that intelligence test, or IQ change. So the procedure for the training group, the way this worked is they came into a lab every day for a half an hour a day, and they engaged in a memory training task. And I'll show you more specifically on the next slide what that looked like. The control group, importantly, did nothing. And that's not a great control group. And we'll come back to a discussion about why that's not a good control group in a moment. And again, the dependent variable is IQ change, the difference between the score on the IQ test post-training versus pre-training. So this study was conducted by Yaki et al. I know that looks like Jagi et al., but it's pronounced Yaki et al., 2008. And what I'm depicting here is a memory task that we refer to as the NBAC task. And in the NBAC task, subjects are presented with a stream of stimuli, and they have to detect when the current stimulus matches the one NBAC in the stream. This is a particularly difficult version of the NBAC because it has two components to it. One is visual, one is auditory. So in the visual task, subjects are seeing squares pop up in different locations on the computer screen. and they have to detect when the square is in the same location as it was n back. And in this case, I'm depicting a 2 back task. So here you see a visual target because it matches this location, matches the one 2 back in the stream. They also had to monitor an auditory stream. So they were listening to a speaker say letters over headphones. And again, here's an auditory target because the C matches the auditory stimulus 2 back in the stream. So here is an example of a 2 back target. That's when the subject would have to say, yep, that matches in both the visual stream and the auditory stream the stimuli that came 2 back. This is thought to measure an individual's short-term or working memory because the subjects have to continuously update both visual and auditory information, maintain that information, and make a response when both match the stimuli n back in the stream. This 2 back task is actually pretty easy. If you tried it, you could probably get about 100% accuracy in just 2 back. And that's what subjects did in the Yaki et al. Experiment. And if they got up to about 100% in a block of trials, then the n was incremented to 3 back. And subjects would practice that, and once they got proficient on 3 back, it would go to 4 back, and so on and so on and so on. And that's the working memory training. So subjects would do this for a half an hour a day for weeks. The question is whether this would enhance their intelligence. We know that it will enhance their performance on this task, but will it enhance their intelligence? So first, this is just a graph showing people's performance in the n back task over time. So what I'm plotting on the x-axis, and here's the x-axis, is just the training sessions. So after this one session, you see subjects are only around 3 back. That's pretty normal. But what you see is over many, many training sessions over weeks, subjects get up to like 5, 6 back. I've been doing working memory studies for 2 decades. I can't imagine myself doing 5 or 6 back in the n back task. It's very difficult to do. So these people, they trained something. I'm not sure exactly what they trained, but they trained something and they got really good at this task. The question is, did they do better on the intelligence test? Well, here are the results from Yaki et al. That show the improvement in intelligence. This is a little difficult to see, so let me walk you through these 2 graphs. So they plotted their results in 2 different ways. In the graph on the left, what they plotted is the change in intelligence from pre to post for the 2 different training groups. So here, before training, that's the pre, there's no difference in the performance score. That's the intelligence test. So there's no difference between training and no training before the experiment began. That's not surprising. We had random assignment to conditions. It should be the case. What's interesting is this result here is people in the training group, their intelligence scores increased more so than subjects who were in the control group. Subjects in the control group went up a little. That's probably just a practice effect. But people in the training group went up even more. So there's some evidence that this working memory training seems to enhance intelligence. In the graph on the right, what we're seeing is the enhancement of intelligence as a function of time training. So what Yaki et al. Did is they had 4 different groups of subjects train in the working memory training procedure. Some of them trained 8 sessions, some of them 12, some of them 17, some of them 19. And what they're plotting here is the gain in intelligence. So that's how much did they increase pre to post. And what you see is sort of a dosage function. So the more subjects trained in the working memory training experiment, the more their enhancement on the intelligence test. So there's this nice linear function. So this is more convincing even than the initial result, that it seems to be really yoked to the amount of training that subjects receive. Now, I mentioned there's one sort of limitation of this study, and that was that the control group did nothing. So the working memory training group, they came to a lab every single day, spent a half an hour a day there for weeks, and then did the post-tests and did much better. The control group did nothing. All they did was take the pre-tests, they went away, they never saw that lab again until they came back, weeks later and did the post-tests. This is problematic because it introduces potential confounds. So just by going to the lab every day, you could become more familiar, more comfortable in that environment. You are performing a task, this NBAC task, and you're getting better, so you're being rewarded for performing well in that environment. So then when you go to sit down and take the post-test in intelligence, you might do better just because you feel better in that environment, you feel more confident about your abilities in that environment, and just that might explain why the training group did better on the post-test than the control group. So a better experimental design here would have been to have a control group that also went to the lab every day and engaged in some task that was rewarding and made people feel better about themselves, but didn't engage working memory. And in fact, there are some labs that are doing that type of work now, and they're not replicating this result. So the jury is still out, in fact, whether this working memory training of the type I showed you here really works or not. Because in this study I showed you, there might have been confounds. It also wasn't double-blind, right? So the experimenters knew that these subjects were engaged in a working memory training task. The experimenters knew, the subjects knew, and the experimenters clearly wanted a particular outcome. They wanted this to work. They wanted to be able to show that their working memory training paradigm could boost intelligence. Again, that could make them very friendly to the subjects in the training group as they're performing the intelligence tests after training, and just that friendly environment might make people feel better and do better on the intelligence test. It would be better if the experimenters who were administering the tasks didn't know who was in the control group, who was in the training group. That would have been a better design. And again, as of today, as I'm doing this in August of 2012, the jury is out on whether this working memory training stuff works in enhancing intelligence. So to wrap up this first segment, the power of randomized experiments is they allow for the strongest arguments or strongest claims we can possibly make about causality. That is, about mechanisms that link independent variables to dependent variables. And my whimsical phrase is, it's our best way of getting at why stuff happens. And if we can understand why stuff happens, we can predict stuff. If we can predict stuff, then we can prevent bad stuff, like polio, or we can promote good stuff, like intelligence, if that working memory training stuff is working. And for it to work, we have to have true independent variables, and I'll explain that a little bit more in the second segment. We have to have random representative samples and no confounds. And again, that's impossible, but good experimentalists, we try to do our best to eliminate those confounds. So to summarize, these are the important concepts to take away from this first segment: random representative sampling, independent dependent variables, double-blind, single-blind experiments, confounds, and causality.